Hello everyone, I'm Dr. K. Nagalakshmiya. This video series is designed for professionals and students who are working and wanted to work in RF and microwave antenna design domain. So this video series is designed such that first we'll discuss theory concept related to the specific concept discussed in that video, and its related design will be designed in simulation tool CST Microwave Studio. So we'll learn through practical design. So here the course content the course content is planned in this way. So we'll discuss in this video related to antenna basics, and there's some small theory about dipole antenna and design of dipole antenna. The later videos will go ahead with loop antenna and microstrip patch antenna. Related to microstrip patch antenna, what are the types, techniques, all these things. It will again a series of videos. Then later we'll switch into slot antennas and antenna arrays. Like we'll take first with simple dipole antenna, and we'll analyze what is the array concept and all. Or we can take a patch antenna. With that, we can try. So these combined together will take up and we'll complete it. Then later, we'll design about how to design feed for the antenna array in case of series fed array, or in case of corporate feed. All these things we'll discuss here. While designing feed, how to design power divider, and what is the design procedure, with which way it will be good, or in which way we have to proceed. All these things will be discussed here. And in the later sessions, we'll go ahead with wideband antennas like bandwidth enhancement techniques. So here we'll discuss about all the wideband antennas and bandwidth enhancement techniques. Then later we'll discuss about gain enhancement techniques like placement of superstrate materials, are going ahead with antenna arrays. All these things we'll discuss in gain enhancement techniques. Later part, we'll go ahead with monopole antennas, which are wideband antennas. So there's a simple type of wideband antenna where it doesn't bother about radiation pattern direction. So its directionality property will least think of about. And once monopole is completed, we'll go for wideband antenna techniques like same printed monopole. This is like metallic monopole, and we'll think about and design about printed monopole antennas. Then like uh, Yagi Uda, biconical, discone. These antennas will discuss. Not every antenna is having same radiation pattern, same properties. So we'll discuss one by one in the later part. And at the end, we'll discuss about dipole antennas, which are a novel techniques like combination of magnetic and electric dipole. So we'll have both magnetic dipole as well as electric dipole. Magnetic and electric dipole combination. So with this combination, we can achieve wide bandwidth. So what are the techniques we have to use, and in what way it will be useful? We'll discuss about this. So this is a course structure which, or video series structure which I have followed. So if you have any suggestions, you can give your suggestions from your side. Then later part will continue with whatever the suggestions you people are giving. So according to the suggestions, we'll continue this series. So in the first part, we'll just discuss about what is antenna, and this entire series is about antenna design only. So we'll try to find out what is this antenna. So antenna is nothing but a transducer. It's a transducer, meaning to say which converts one form of energy to other form of energy. So here in our case, in antenna, what way it is transducing the power. So in general, the antenna is like, it's a transducer between a transmission line and free space. So inside the transmission line, we'll have guided waves. So here it is guided waves, or guided EM energy. Guided EM waves or guided EM energy is transduced, means converted into free space waves, which is like generating some disturbance in free space and creating free space EM waves. So antenna is nothing but, it's a transducer which converts guided EM waves. So converts guided EM waves into free space EM waves. Or you can say guided EM energy into free space EM energy. This is a simple definition which in every textbook they'll follow. So we can define in one more way, like it is a matching device between a 50 ohm transmission line and free space. Free space, which is like 377 ohms impedance. So you can directly say it's a transducer or an impedance matching device between 50 ohm transmission line and free space. So this we can represent in the form of a circuit. So here we'll have a source, and this source is connected to a transmission line, and this transmission line is transforming the energy to free space. So while transforming this energy, we'll have losses to represent uh, those losses. We are taking RL plus JXL. So real part as well as imaginary part, both will be there. And it will have some radiation resistance, which is connected to free space. And this radiation resistance is grasping the power and radiating into free space. So here, what is the importance of this RL and JXL? So this RL represents losses due to conductor or dielectric, whatever we are using in designing the antenna, and losses due to impedance mismatch. So while designing, might want to connect 50 ohm to exactly 50 ohm, but it won't be possible exactly 50 ohm. So there will be some reflections. So that reflections we have to include. So that is RL. RL is nothing but this reflection and some ohmic losses, which are like conductor and dielectric losses. And this JXL is a term which is representing storage inside the antenna. It may be due to Evanson modes, or it may be due to the conductor spacing is less. Because of that, it might having some capacitive kind of effect, which is like storing the energy. So those things we have to make into consideration. So for that, we are uh, taking consideration of this JXL term. And one more term is radiation resistance, which is like how much power is radiated into free space. After these losses, how much power we are giving and how much power we are radiating. That is represented with this R. So this is a simple implication of all the equivalent circuit parameters. So while this is about a simple antenna, so why and in what way we can create a radiation? So what we need for creating radiation from an antenna? So to create radiation, we should have either time varying currents, meaning to say DC currents are not positive. DC currents, they can't be radiated. Or we can say like to create radiation, we should have accelerated or decelerated charges. So if we have charges, if they are moving with uniform velocity, then there won't be any radiation. So to create radiation, we should have acceleration or deceleration. Like when you have a straight conductor wire, you won't have any radiation. If we have a conductor which is bending, so the acceleration, whatever you are saying, it is flowing with uniform velocity, so it won't get any radiation. But in this case, when it is going with uniform velocity, you are getting some obstruction, because of which it might get decelerated and will get radiation from this point. So we need a discontinuity to get radiation. So this is a main thing which we need for getting radiation. So next, this is simple concepts which I just want to discuss, and later we'll discuss about antenna parameters. What are the parameters important for antenna designer? As an antenna designer, you should know all these parameters. So once you know these parameters, we can directly jump into the antenna design and we'll get a clear knowledge about antenna design. So first parameter which we are going to discuss in this is radiation pattern. So what is a radiation pattern? Is like it's a graphical representation of power or electric field intensity variation at a constant distance from the antenna. So we can say directly, so it's a graphical representation of power or electric field intensity. You can take anything. Variation at a constant radius from the antenna. Say suppose if I have one antenna like this, which antenna I don't know. So for now, I'm just taking it as a general case. See, if we have an antenna, so for this antenna, if you take a distance of radius r, and around this antenna, what is the field intensity at distance of r? So here the intensity might be P1. Here the intensity might be P2. Here intensity might be P3. So if I take a radial path, which is around this, so you'll have all intensities like P4, say for P5, P6, and so on up to whatever the Pn you have. So this we can represent like this based on the intensity at all points. So here you'll have at the same distance only, but at certain theta comma phi. So for certain theta and phi, this is we are taking it as a certain radius, and at certain theta comma phi, what is the intensity? That intensity we are plotting at a constant distance. So I'm plotting P1, P2, P3, P4. You might have ended up like this. So this is a pictorial representation of its intensity over a distance of r, constant distance of r, and in all directions of theta and phi. You can say like this is a simple representation which we are saying. This shows the basic antenna radiation pattern. So based on the parameters which we are plotting, we can classify that radiation pattern as power pattern or field pattern. If it is power intensity, you can say power pattern, or if it is a field intensity, you can say it as field pattern, or you can say power pattern in dB, in decibel scale. That is also there. So the basic term defined in radiation pattern, what we have to consider is beam width of the antenna, or you can say half bar beamwidth of the antenna. This beamwidth or half bar beamwidth of the antenna is defined as angular area, angular distance over which the field amplitude varies from maximum value to 0.707 times maximum value. Meaning to say, if you are plotting electric field intensity, say suppose like I'm plotting here electric field intensity in this fashion. So if I consider this as a maximum to 0.707 times, means 1 by root 2 times. Wherever you are getting this value as an intensity, so the range of theta or angular distance, this theta you can call it as half bar beamwidth. So the range over which it is the field intensity is varying from maximum to maximum by root 2. That is for field. If it is a power, then max to max divided by 2. This is related to power. The same thing, if I make field E, value is E by root 2. If I take power P, which is equals to E square term, so which is like E square by 2. The same thing we are talking, but it is showing in different fashion. Here it is 0.707 times, here it is 0.5 times only. There's no variation. It is simply the term square. Second thing we can define in terms of dBs also. So the same power, if it is represented in terms of dB, then in that case, max to max minus 3 dB. So the range angular variation, the angular distance over which the power in dB varies from max to max minus 3 dB. We can call it as half power beamwidth of that antenna. So this is about beamwidth and radiation pattern. So here we'll get one more term called pattern lobes. So the general rectangular plot of a radiation pattern will have maximum at the intended direction. We'll call it as 0 degrees. And then it's keep on reducing till it reaches plus 180 and minus 180. You can call it as 0. So the main power is concentrated in this lobe. So maximum power is concentrated in this lobe. So we can call this as main lobe. In any radiation pattern, wherever you are getting maximum power, that we can call it as main lobe. Other than main lobe, all other lobes, we can call it as side lobes. Or you can say minor lobes. This main lobe, you can also call it as major lobe also. Sometimes they'll call it as major lobe or sometimes they'll call it as main lobe. So it won't be any problem. And here the lobe which is in the back side. So this one. Say suppose if it is like ended like this and ended like this, these two combined together will form one lobe. The lobe which is at 180 degrees, you can call this as back lobe because it is present in the back side of the antenna. Sometimes when you are having directional antenna, then it is possible. When it is omnidirectional or isotropic radiation, then in that case there is no back lobes and all. So we'll discuss further in the upcoming time. So here we can define. So here this is the maximum value. So we can define half power beamwidth over here. Say suppose this is the maximum and max minus 3 dB, one term, max minus 0.5 times, or you can say like wherever you are getting 0.5 times maximum value, or you can say wherever you are getting 0.707 times, this is maximum power, and 0.707 times maximum E field intensity. So all these terms are representing the same thing. So this beam width range, we can call it as half power beam width. There is one more term which is like first null beam width. It is defined as the angular distance between the first nulls, meaning to say first low value, and then it is starting increasing. So we can call this as first nulls. So this beam width, you can call it as first null beam width. So in radiation pattern, we'll have all these things. If we have these parameters, we can design all the antennas max. And if you're getting more content, then that content will be discussed along with the design, wherever we are getting the radiation patterns. In that, I'll discuss about what is the absolute value, what is polarization, all these things we'll discuss with the designs. So here, based on the directional properties of the antenna, there are three types of radiation patterns. So this is one type. We are saying directional antenna. So we'll have three different types of radiation patterns. One is isotropic. The other one is omnidirectional and directional. So we'll have these three radiation patterns. So I'll just show you the image all combined together. So here we'll get all the radiation patterns in one single click. So here isotropic, meaning to say the intensity is spread over all directions with equal intensity. So here, if you see this green color, the electric field intensity is same in all directions. So this is like a football or any ball or sphere where all the all over the top it is having same intensity. As we reduce the radius towards the center, the intensity varies. P varies with a radius. This is isotropic radiation. It's an ideal case and it is defined defined as the radiation pattern in which will have radiation intensity over the sphere is same and which is ideal, which it is not exist if we have a positive charge. The general electromagnetics, electric field intensity from this positive charge, if you have only positive charge, this intensity is same over all over the sphere if you are placing this charge inside a sphere. So that kind of pattern is isotropic radiation, which is ideally exist, and we'll take this as a reference to define directional properties of all other antennas. Second one is omnidirectional antenna. So omnidirectional radiation is something like apple shape, like this. So here the radiator is placed like this. So simple example is a dipole antenna where we'll excite at the center. The radiation comes all over this side and it won't radiate in this direction and in this direction. So nulls in Z positive and Z negative. And in remaining all directions, the intensity varies. And we'll take this as a reference. We'll define this antenna is having somewhat higher power in this direction and lower power in this direction. You can say lower power in this direction, like Z positive and Z negative. So this variation of electric field intensity plotted over all theta and phi at certain radius. We are calling it as a radiation pattern. Third one is directional antenna, in which case the antenna energy is directed towards certain direction, certain theta and phi. It's not like omnidirectional, omnidirectional is also some kind of directional part. It is having some kind of directional properties when compared to isotropic. But directional antenna case, we are concentrating maximum energy in certain direction, while concentrating maximum energy in certain directions, the other directions you'll have intensity but lesser than this maximum value. So this is about the radiation pattern. So next we'll discuss about field regions. So this also I'll explain with a simple image. This I'm getting it from Google only for convenience purpose. We are doing this. So here, whenever an antenna is radiating, it will start radiating in the form of spherical waves. So here, these spherical waves, as they are progressing from the antenna toward a distance, over the distance, the field is acting like different way. So in the initial region, this is a reactive near field region where the energy is concentrated in the form of evanescent sorry evanescent waves, meaning to say these waves will have beta equals to 0, no propagation. No propagation in the sense it is having storage. So in this region, reactive near field region will have only storage. That is why this is reactive. After this 0.62 times square root of um, d cube by lambda, after this much distance, this is radiating near field. Here we'll get radiation, meaning to say we'll have propagation. Beta is something which is not equals to 0. And here the waves are in the form of spherical waves only. Over this distance, if we plot a straight line, it won't have equal intensity because of this spherical nature. So here we can say this is having spherical waves, which is like we won't have plane waves. So plane waves will have equal intensity on one plane. So if I draw a plane, the intensity of radiation has to be same. So that region is covers between these 2 points where end of a reactive near field comes and start of radiative far field starts. So between these two, you'll have radiating near field. We call these entire thing as a near field. So for antenna testing purpose, we always use far field. So the far field is defined by this term 2 times d squared by lambda, where d is the maximum dimension of the aperture. So if you take a rectangle or square, we can't say this is the maximum distance. So this term is not maximum distance. So maximum distance is corner to corner distance. So this term we can define as maximum length or maximum dimension of the aperture. So based on this, we have to calculate the far field region. So in the far field region, we'll have plane waves where the intensity of radiated field is constant. So this is about our field regions. And next, based on the directional property of the antenna, we can define one parameter is called directivity. So why we need this term directivity is how much directional property your antenna is having when compared to isotropic radiator. So if you have an isotropic radiator, then isotropic radiator is radiating in all directions. So when compared to this isotropic radiator, my designed antenna is having a directional property. If I take this as a reference 1, so when compared to isotropic 1, I'm getting my power intensity radiated in this certain direction. So here if you say 1, here this will be like 1 times directional property D. So here how much efficiently your antenna is radiating and how much directional it is. These terms will define in terms of directivity and gain. So one term is directivity when compared to isotropic radiator, how much extra intensity you are able to achieve at this point. So you can directly define it as ratio of radiation intensity of this antenna. You can say DUT to radiation intensity of isotropic radiator. So if you have an isotropic radiator, say suppose your intensity might be E. So the isotrope, this DUT will have a directional property multiplied by whatever the isotropic intensity you have, that one. So here you can directly define it's a just a term, a ratio, which is like how much extra power you are concentrating in this direction when compared to isotropic radiator. So next important parameter is the antenna efficiency, which implies how effectively the antenna converts energy from one form of energy to other form of energy. So efficiency is nothing but how efficiently, how effectively you're converting one form of energy into other form of energy. So here we'll define total efficiency which is equals to, it is like conductive and dielectric. Efficiency multiplied by matching efficiency. So in antenna equivalent representation, we have given two terms RL and this mismatch, which is like reflection. So based upon these two things, we can define one more term which is important for your antenna is gain. So gain is nothing but its multiplication of directivity and efficiency. So here the gain term itself is defined as directivity and efficiency. Well, while designing antennas, we might have come across around gain or gain IEEE, realized gain or absolute gain. So these so here term gain is defined as directivity multiplied by efficiency due to conductor and dielectric efficiency. So if your antenna is not having any conductor losses or any dielectric losses, your directivity is approximately equals to gain or gain IEEE. So here they won't consider about S parameters or matching. How much power is coming to the antenna, how much power is radiated, they won't bother about this. So here they'll only consider what is the aperture size. So if I have some aperture, so this aperture will have certain directivity. So this directivity multiplied by efficiency of the antenna because of conductor losses and dielectric losses combined together is gain term. The other term is realized gain is the total gain. You can say like directivity multiplied by total efficiency, or you can say like gain multiplied by matching efficiency. So if I have antenna like this, source is connected to antenna. So gain is related to only this part. if we have any losses or any storage, this gain term will know. And this entire thing from source to up to radiation, like mismatch, as well as conductor losses, as well as dielectric losses, all these things comes in realized gain. So whenever we are designing an antenna, we least bother about gain term. We have to bother about realized gain term, which is like whether it is positive or negative. You might have gain as a positive, but you doesn't have impedance matching that will give realized gain as negative. So that's the only implication we have. And that's a thing we have, this relation between gain, directivity, and realized gain. So here we have directivity, gain, and realized gain. So whenever you are designing an antenna, we have to concentrate most of the time on this term. The last parameter which we are going to discuss is bandwidth. It's nothing but band of frequencies or the range of frequencies over which the required standards are met. So here the standards are nothing but pattern beam width. So we might need 3 dB beam width as like 30 degrees or 60 degrees over a band. So over which band of frequencies we are getting this much half power beam width, or we can say impedance bandwidth. So we can hear this term pattern bandwidth or impedance bandwidth. So the same thing here, the range of frequencies over which the source impedance is matched with antenna impedance. So that is impedance bandwidth. So these all are the important parameters which we should know while designing an antenna. So we'll stop here. I'll start one more video on dipole antenna design.